Just a minute. Let's expand the screen and start the slideshow from the current slide. All right. Now, let me go over a couple more announcements. My office hours this week are crazy, okay? And it all stems from the fact that I've got a nephew getting married in Dallas, Texas this weekend. And stuff starts on Friday, so we have to fly on Thursday. Now, don't start worrying, because it's not going, won't be as bad as you think. But because I will miss my differential equations class and my linear algebra class on Thursday, that means we're going to have a double class today. Let's see which one. I think linear algebra. Okay? So normally I'm through today at 12:15. Today it's going to be 1 o'clock. Okay? No, I'm sorry. 1:30. 1:30. Okay? Then tomorrow, more of a normal day. Okay? Office hours don't change. But then Thursday, we fly out on Thursday. I know y'all are getting this sad expression on your face, but I wanted you to say, don't worry, I'm going to come in and teach this class and then go home and we'll fly out. So I know you were concerned, okay? But don't fret it, okay? I'll be here, knock on wood, okay? And all right, I can't see in this bright light. Diana came in. Has anyone else come in since the call dropped? Okay. So, the rest of my office hours on Thursday, none. Okay. Normally it's 12:15 until, well, Tuesday it's going to be 1:30 until 4:45. Okay. Thursday, no office hours at all. I come in, teach this class, and then go back home again. Okay. So we have no office hours on Thursday. Friday, of course, I'll be in Dallas. No office hours that day either. So I've got to take personal leave for those portions of Thursday and Friday. Then next week, Monday's normal. Tuesday, we have a double session for the differential equations class, and then a single session for the linear algebra. So again, my office hours won't start until 1:30. Okay, but then 1:30 to 4:45. And after that, we're back to normal, sort of whatever normal is. Well, and one exception there, too. Now, this hasn't been confirmed yet, but I'm supposed to start a new round of treatments next Friday, not this Friday because I'll be out of town. And because it's the first time I've had this drug, it said it's going to take 6 hours for the infusion. So I will not be here much of Friday. If they've got to start at sometime in the morning, so the odds are I won't be on campus at all Friday. It's a Birmingham campus because I have to go in an hour ahead of time to get the blood work done. So the chance of my being on campus at all on Friday, that's next Friday. Okay, this Friday I'm not going to be there at all. The following Friday probably not either. Then the following Friday after that, I have another round. The first 2 rounds are 1 week apart, and then after that it's 2 months apart. Shun's here. So I don't know what time. They haven't given me the times for either of those 2 appointments. But the odds are those Fridays may be iffy whether I'm on campus or not. All right. Enough of that. Any questions for anything we've covered so far? I wanted to say this. This class has been pretty good about getting papers in. 3 papers in out of a class of 20, what is it now up to? Was 25, 2 no-shows, that was 23, and I think 2 withdrawals, 21. So down to 21 students and 3, that's not great, but it's better than most classes. So folks, please get your papers in. Remember, the month of October is a 2-point month, 2 bonus point month. Okay? I don't have to say it here. Yeah, you got it. Okay? And the second thing I was going to mention is the quizzes, are the quizzes. This class has been really good about getting quizzes in so far. So please, I'm probably preaching to the choir here, but please try to get, another one, okay? Please try to get your, oh, yes, okay. All right. Please try to get the quizzes in, because the sooner I get the quizzes in, the sooner I can get them back to you and you can see what you missed. Now, as soon as you see your grade on Blackboard, you can come see what you missed right away. I just can't give your paper back to you. I can give it back to you to review, but I don't want the correct answers floating around there when there's still people who haven't turned them in. Yes? I'm sorry? Oh, absolutely. I want to get them out of my stack as soon as possible, you know? Okay. Not that I don't like having your papers, but, you know, I don't want them long. Okay. Let me find you. Is it Courtney? Is it Courtney? Yeah, okay. I want to make sure I got the right person here. All right, good deal. All right. Anyone else come in since I called roll? Any other questions before we get going? All right. Now, this slide is from the old book, and they're referencing example 5. Your book, of course, we did 5 and 6, but we finished both of those last time. But it says, in these examples, you formed the composition of 2 given functions. Remember, we did that last time. No questions on that? Okay. In calculus, it is also important to be able to identify 2 functions that make up the composite function. Okay? For instance, here's a function, h of x. 3x minus 5 raised to the 3rd power. Is that a composition of 2 functions? Yes. There's the linear function, 3x minus 5, and then there's a cubing function, raising that to the 3rd power. Okay? So that is a composition of f of x, which is the cubing function, and g of x, which is the linear function, 3x minus 5. So you could write this h of x here as 3x minus 5, or cubed, that's exactly what it is. But the 3x minus 5 is your g of x cubed, but the cubing function is f, so that's f of g of x. Okay? So when you're doing this from scratch, you don't have to go through all that. Don't scratch too much. Okay? Notice what the innermost function is here. 3x minus 5. That's the innermost function here. The outermost function is the cubing function. That's your f, cubing function. Does that make sense? So you basically are decomposing the function. It's a composition of 2 functions, the linear function, cubing function, and now we have figured out how to break that down into the 2 functions. Have any of you been exposed to calculus? You have, okay. Do you remember the chain rule? That's what they're talking about here. That's exactly what they're talking about. Okay. Basically, to decompose a function, a composite function, look for the inner function, that's what I was just saying, and the outer function. And the function h, g of x, the linear function, 3x minus 5 was the inner function, and the outer function was the cubing function, x cubed. Okay? And then they don't do any applications. Okay? I mean, any examples. They have one in the text. Sorry. Let's do that application. I mean, that example. The next section is application. All right. Ooh. Okay. Write the function h of x is equal to 1 over x minus 2 squared as a composition of 2 functions. And let me tell you this right off the top, there's more than one correct way to do this, okay? You just have to figure out what you think is the innermost function and what you think is the outermost function. Okay? How would you begin? That sounds like a good start. Let g of x, and we're going to say that, I'm assuming that's your innermost function, equal to x minus 2. You don't have to call it g of x, but you can. That's perfectly fine. What then would be f of x? Okay. Now, actually, if you do it x squared, which is a fine thing to do, what do you want to name that? F of x, you said? Okay, f of x equal x squared. That's fine. Then, actually, you have a composition of 3 functions because there's one more. The reciprocal function. 1 over x squared, right? You could have either called that your x, 1 over x squared, or you could have another function, no, that's already h of x. I'm running out of letters. E of x? Yeah, let's call it e of x. Okay? That's a strange thing. I don't like using e because I think I won't use e. Because there is a function named e. That's the exponential function. We haven't gotten there yet, but we will get there. Let's call it d of x, okay? Even though that's usually something else. And that could be 1 over x. So you see, the innermost is this one. The next innermost is that one. And the third one is the reciprocal function. So you could have up to 3. Or 4. I mean, any number. Or, like I said, there's several ways to do this. Another way would have been g of x equal x minus 2, and then f of x would be 1 over x squared. And then you could have done it with 2 functions. Or you could have done g of x is equal to x minus 2 squared. What would your f of x have been then? 1 over x. You got it. So you see there's several ways you could approach this. When y'all who had some calculus, did you do integration or did you just do differentiation? Huh? Just differentiation. Yeah. When you get to integration, you also have integration by parts, which breaks apart these functions like this too. Actually, that's more multiplicative, but you can do that. So you see there's several ways to decompose a function. All right. The book chose how did they choose that? Okay. Yeah, they did the g of x equal x to the minus 2, just like we did. They did the middle way. And then they had f of x equal 1 over x squared. Now, another way you can write the f function as x to the minus 2. Y'all know that, don't you? That negative exponent in the denominator, if you move it upstairs, it becomes negative with that. Or if it was a positive exponent here, you move it downstairs, it becomes, you flip the signs as you cross the dividing line. So that's how they did it. All right. Were there any other examples? No. The next is application. Maybe not the best time for a dumb story, or is it? Oh, okay. If it is, we can do this. We're talking about arts and humanities. This sort of has some tinges that way. Do any of you know who Beethoven was? Now, it's not the big St. Bernard, not that one. Okay. All right. Great composer. One of the greatest of all times. In fact, his 5th symphony. Dun-dun-dun-dun, dun-dun-dun-dun, beautiful, just a fantastic, powerful work. I'm not sure any other symphony has even come close to that symphony in power and beauty. I mean, it's just incredible. And he was pouring them out. I don't know how many he got up to, but he was very prolific composer. Now, as far as I know, I don't know this for a fact, but from what I understand, he probably never married. He was just so into his work. But here's a side question here. Anyone tell me who won the Grammys 5 years ago? I don't know who won them last year, but I thought if any of you are into music, guess what? Very few musicians have a very prolonged lifetime of fame. I mean, people know about them, but taste change and things like this, it happened back in Beethoven's time too. As he was getting older, people were less interested in the big booming symphonies and wanted other stuff, and people got away from those kinds of things. So Beethoven was quite a good musician, but his style of music sort of went out of fad. Back then, there was no social security system. There was no social safety net, and he lived on selling his music. That's how he supported himself. And when nobody was buying, and he was getting older, he became quite destitute. Now, he also had physical problems. I don't know all of them, but I do know, if I've heard anyway, he was going deaf. Just imagine that, a musician, someone who composes music going deaf, that's a pretty tough combination there. And what I've heard is that he had them cut the legs off of his piano because he composed on the piano and sat on the floor with the piano on the floor and heard the music through the vibrations in the floor. He was that good, okay? Still was producing music. The trouble is no one was buying. But he did live to be fairly old. But by the time he died, he was destitute. Nobody knew of him anymore. His music was out of fad or favor, and no one paid him any attention. He died a pauper and was actually buried in what they called the pauper's grave, the potter's field. Just a thing. Well, sometime later, his music sort of had a revival. People got a little tired of that new stuff, and said, this isn't nearly as good as what Beethoven used to write. Whatever happened to Beethoven? And they started looking around trying to find out, and found out he had already died and no one knew about it. And that he was buried in this potter's field out in the sticks somewhere, where no one went. They said, no, this can't happen. He was quite possibly the greatest musician of all time. So they had to go through all sorts of legal ramifications to go out, and they said his tomb needs to be at some place people can celebrate, not the potter's field. So they got permission to go out and exhume the casket and take it and put it in a more prominent place where people could come and pay homage to this great, great, great composer. But when they were doing that, finally got all the permission, the poor old grave diggers were out there digging them up again, and stuff, and they lifted him. From what I understand, a pretty heavy guy, lifted it up, and just about the time they got him to the top, one of them dropped it, and the lid popped open, and there he sat, erasing music like crazy on score sheets. What was he doing? Say again? He was decomposing. Never mind. Okay. All right. All right. That's enough for decomposition today. All right. You said you wanted a dumb story. You got it. Okay. All right. Okay. What did you do in math class today? Okay. Let's hit some applications of this. All right. And this is real world. Okay. The other was a little bit of truth mixed with a whole lot of other stuff. Okay. Here's an example. This is a very practical example, especially with the big holidays coming up at the end of this term. The number n, and this is true, the number n of bacteria in a refrigerated food is given by this thing. N is the number, and capital T is the temperature of the food in degrees Celsius. Okay, we usually use Fahrenheit, but this is Celsius. And this is number of bacteria is 20 times that T squared minus 80T plus 500. But this formula has a restricted domain. Remember that? The domain is restricted by the problem. Its T is between 2 and 14 degrees. Now, just to give you an idea, 2 degrees Celsius is probably about 35 degrees Fahrenheit, which I'm guessing is about the temperature of your refrigerator. Not the freezer part, the refrigerator part. Doesn't freeze food, but it keeps it pretty cold. Okay? So that's normally what it is. Now 14 is getting pretty close to what it is room temperature. 20 degrees is room temperature. So this is going up to probably 50 to 60 degrees, somewhere pretty close in there. Okay? So obviously you've taken it out of the refrigerator here, and this is the formula for the number of bacteria in the food between 2 and 14 degrees Celsius. Okay. When the food is removed from the refrigeration, it follows this. But the temperature, by the way, follows this. Capital T temperature as a function of little t time, okay, where this time is in hours, okay, is 4T plus 2. That's how the temperature increases when you take that food out of the fridge and it begins following this. The temperature increases at this rate. In the fridge, it stays right around 2. But when you pull it out, then it starts warming up according to this. And this is only good for T equals 0 to 3 hours. After this, those boogers are multiplying like crazy, okay? But right now, this works. Find the composition N composed with T of T. See, here we have our N of T, here we have our T of T, but this is capital T of little t. I wish they had chosen something, but it makes sense if you know what they stand for. So find the composition of those two functions. Okay, let's do that first. What do we mean by N composed with T of T? Remember what the definition was? It's what? Okay, except it's N and T now. So that would be N of T of T. Okay? No X's here, but T's. Okay? That is the definition of N of T of T. All right. Now, what do we do first to find that composition? What do we plug in first? The innermost function. So that would be N of, and what's your T of T? 4T plus 2. Okay, and then what do we do with the N function? Oh, I don't think I need to write that again. Okay, let's just, okay, what would that be? What does the N function say to do? What do you start with? 20, okay. You start with 20, and what do you do with that 20? You multiply it by whatever is in here squared, right? So your N of this thing would then be to take 4T plus 2 and do what? Square it. Good. What do you do next with the N of T? Subtract 80 times 4T plus 2. Very good. Okay, and then you do a plus 500. Boy, you already start out with 500 bacteria before you do anything else. Wow. Okay. So that is your, oh well, we got a little bit more to do. We need to square that binomial. So that N of T (20) times, and what is 4T plus 2 squared? (16) T squared plus what? Remember your cross products? Yes. Well, you double the cross product. Remember? Okay. If you don't remember that, you can always go back and FOIL it. 4T plus 2 squared is 4T plus 2 times 4T plus 2. That's what it means to square something. Multiply it by itself, right? And if you FOIL it, what do you get? 16t squared plus 8t plus 8t. That's why you double it. And then your plus 4. Y'all jump right to the plus 4 and forget your middle terms, okay? So that's 16t. So it's 16t squared plus 16t. Now, it doesn't always come out the same number, but ooh, it did on that one, okay? And then plus 4 times 80 times this. What would that be? Minus what? A little louder. Second? 320t minus 160 plus 500. Right? Okay, let's take this to the top up here. N of 4t plus 2 is equal to 20 times 16 is what? 320 t squared plus 20 times 16 is still 320 t plus 20 times 4, 80 minus 320 t minus 160 plus 500. Poor little 500 gets thrown around down there. Okay, you have a few like terms you can combine. 320t. 320t. Okay. 320t minus 320t is 0. Okay. And 580 is 580 minus 160 is 420, right? So these add what? Say again? Yes. Was there a question? Okay. So let's see, this is equal to 320t squared. Your t's went away, and then you had, what would it say, plus 4, what was it, 420? Okay, there's your function. N, number of bacteria, as function, now not of temperature T, but little t time. So what is the, interpret the meaning of that function we just got? This one right here. N of t is equal to this. What's that mean? The number, say it? The number of bacteria as a function of time, not a temperature. This is the number of bacteria as a function of temperature. This is a temperature as a function of time. The composite is the number of bacteria as a function of time. Okay? So in other words, you've just eaten that all you can of that turkey, but there's still a lot of meat on the carcass, and it's sitting there on the kitchen counter, and you're just too full and full of those enzymes and just want to sleep, and you let it sit out there a while. Guess what the bacteria are doing? Multiplying like crazy. Decomposing the turkey, but composing themselves. Okay. So, the number of bacteria are increasing the longer it sits out of the fridge. You put it in the fridge, it's still increasing, but very, very slowly. Okay, when it gets back to 2 degrees Celsius. Okay. Now, based on this function, number of bacteria is a function of time, find the time. So what are we looking for? And what is that represented by here? Which t? Little t, okay, small t. When the bacteria count reaches 2,000. What represents the bacteria count? The n, the function, okay? So what we're saying here is that 2,000 number of bacteria, sorry, there's so much little white space on here to do, is equal to 320t squared plus 420. Okay? How would you go about solving that for t? Okay, subtract 420 from both sides. You really want to do that? You sure you want to do that? Okay, actually, no. In this case, probably is the best thing to do. Let's subtract 420 from both sides. Okay. Yeah, minus the 2,000 if we get them all on the left. But guess what? I was guessing we're probably not going to be able to factor anyway. So this is just as good. So subtract 420. All right. Don't have much room, but here's what we got. I'm going to move this to the other side. So we get 320t squared is equal to 1,580. 1,580. Okay? What would you do next? Say again? Oh, please don't. It's already squared. Not yet. Yeah, divide out that 320. Divide out the 320. So then you have just the squared. T squared is equal to, and someone got a calculator? I can do part of that. What you got? 4.93. Okay. And, but now we still don't have, that's t squared, what we got to do? Now we take the square root, and what do you get? T is approximately equal to? Say again? Okay. I'm trying to, say again? Okay, well, okay, good call there. And what do you get? I can't do that in my head. It's 2 point something. Yeah, the square root of that. 2.4? So it's 2.4 hours. All right, question. We have a plus or minus there. Do you think that's what the bacteria count was 2.4 hours in the past? No, that doesn't make any sense. You don't do negative times, so we lose the minus sign. So it's 2.4 hours. So by the time that sits out for 2 hours and 4 of 60 would be 24 minutes, you're going to have about 2,000 bacteria living in that turkey carcass, right? Now, actually, this isn't really the problem. That turkey carcass was already warm when it's sitting out there after Thanksgiving meal. This is after you put it in the fridge and you pulled it out for supper and let it sit in there. Because then it was starting at 2 degrees. So actually, it was even worse right after lunch. But in 2 hours and 24 minutes, it's up to 2,000 bacteria count. Now maybe your stomach can handle that. I don't know. What was it at time t? At time t equals 0, when you first pulled it out of the fridge, your temperature was 2 degrees Celsius. And at 2 degrees Celsius, when you plug that in here, your count was probably something around 500 or maybe even less. Okay? So it has gone from around 500, maybe even less than 500, up to 2,000 in about 2 hours. And guess how those things multiply? Exponentially. Okay, they are doubling every half life, or double whatever you call it. Yes. What's that? Okay. On this mess, how can you do that? Okay, never mind. Okay. What's that? Yeah, right here. Okay.
It says find the composition of T. We use the 4T plus 2 because that's what T is, right?
All right. Remember what we said last time? I'm sure, were you here last time?
Thursday?
Yeah, Thursday. Okay, you missed it. What the definition of this thing is, N composed with T of little t. Think of that as, this is my little rule, think of this as an of. It's not what it stands for. That's N of T of T. And that's where I believe Brianna got this. So what you do then is fill in the innermost first. So you put this, T of T, inside here. That's what we did here. And then you operate on that with your N function, which is up here. Yep. So that's what your composition is, the outer one of the inner one.
And what did we say the meaning was? The
N was number of bacteria. And capital T was temperature, little t was time.
That was an answer for interpreting this meaning in context?
Yeah, when it said find the composition of this, we did all that work and got down to this right here. N of little t is equal to this. That's what the function was. So that was the A part, ended right there. The B part said, oh yeah, and then interpret the meaning in context. That's what we did verbally. What does that mean? Number of bacteria is a function of time, not of temperature. This number of bacteria is a function of temperature. When you do the composition, that gives you N as a function of time. Number of bacteria is a function of time. That's a lot easier to deal with than trying to keep track of the temperature as it's changing. So yeah. And then we use the B part, using that and plugging in 2,000 for the number of bacteria, find the time. That's it. What's that? Oh. Oh, okay. Yeah, no problem. Any other question? Good question, by the way. A good rehash. Okay. All right. I think that does it. And by the way, there's another example checkpoint right at the bottom. So if you need a little bit of review, as soon as you can after class, do the checkpoint. If you can't, if you have trouble with it, audio video solution, found at larsonprecalculus.com. This guy is good about doing that. So here's how they do their solution. They first, just like Brianna did, the composition of N with T of T is N of T of T. Okay, that's how I read that. Always do that first. Then plug in the innermost function first. Your T of T was 4T plus 2. And then you operate on that with the N function. Says take whatever inside here, multiply it by 20, square it, subtract 80 times it, and add 500 to it. Well, they squared it, they distributed it, they distributed it one more time, and now they combine like terms. And just like we saw, the plus 322, that won't always happen this way, you were very fortunate. 320t minus 320t adds to 0. Combine the constants there, and what you get is 320t squared plus 420, I'm sorry. So that's your N, number of bacteria as a function of time, and that's what they say that. The composition N of T represents the number of bacteria in the food as a function of the amount of time the food has been out of refrigeration. Whereas the first N that we had was a function just of temperature, which is a harder thing to measure. Time's much easier to measure. If time's following that formula we had, 4T plus 2. Okay. The bacteria count will reach, this is the B part, 2,000 when your N of T, as a function of time that we calculated, found what that was, is equal to 2,000. That solved that equation for T. Boy, they sure showed you how to do that, didn't they? And we came up about 2.2 hours. Evidently, someone's calculator.
It says 2.9, but if you square that, I feel like it can't be more than 2.3.
Okay, yeah, so it's 2.2, yeah, not 2.4. Yeah, calculator error, okay. Not an operator error by any means, okay, yeah, no, okay. All right, 2.2 hours, which would be 2 hours and 12 minutes before you got 2,000 bacteria crawling around in that turkey, okay, if it's turkey, okay. All right, does that make sense? All right, note that when you solve the equation, you reject the negative value because it's not in the domain of the composite function. That was the other reason. Remember, the time way back at the beginning, ooh, too far. At the beginning, time is 0 to 3. Negative 2 is not in there. So that's the other reason you have to throw out the minus. Yes?
I just got a question on terminology. Is there any other terminology for as far as values? Like,
For what?
as far as values in equations, like do they use roots?
Use what?
The word roots as another
Roots.
terminology for values?
Right. Okay, no, root being when you take a square root, like you did here when y'all were doing it. When you had this, you take a square root of this, and you got 2.2. Okay. Okay.
I was just trying to get
What's that again?
I couldn't find anything to help in the same terminology as what we were doing and find all real values.
Oh,
But anything that would come up would be like, would you like to find all the real roots?
okay.
of this
Okay.
equation? And I'm just like, I don't know if that's the same thing.
Okay. Sometimes they do use that. Okay, I thought you meant this problem particularly. Yeah, the roots of equation are also quite often called the zeros of the function, and they're called the solutions of the equation. Yeah, all those names mean about the same thing. Values, roots, solutions, In other words, find the answer. Okay, when these conditions are met, find what will make it true. And that could be called a value, a root, solutions. There's a lot of different terminology you can use. Okay? All right. That ends it for 1.8. There's only 2 vocabulary questions here. Let's see if we can get these done. 2 functions, f and g, can be combined by the arithmetic, I'll call it that. There's a better pronunciation to it. Operations of 4 of them. What did you learn to do in grammar school? Add, addition, subtraction, multiplication, and division. Your arithmetic or arithmetic operations. That's what I was trying to say. Number 2, the blank of a function f with g is f circle g of x, and that's defined to be f of g of x. What's that blank? Composition of the function. Very good. Remember, no, okay. All right. Do number 3, homework exercises. Do any of the odds 5 through 11. And there's like 4 parts plus a question, domain. So really 5 parts to each of those. Okay? Then do any of the odds 13 to 23. That's more of those arithmetic combinations. Then do 25. That's doing a graphing. And the graphing only works well with the sum when you're adding. Subtraction, you kind of can do multiplication, division, graphing. It really doesn't give me any insight at all. It just gives me a headache. No, I'm not. Okay. And then there's more graphical reasoning, 27 or 29. It says you might need a graphing utility here. You can do it without that, perhaps, but try 27 or 29. Then 31 and 33 are composition of 2 functions, but they're 3 parts each. You can compose f with g, or g with f, or g with g. That's sort of crazy, but you can do it. Or f with f. They didn't ask you to do that. Then, finding domains of functions and composite functions. Again, there's 2 parts there, plus the domain. So do any of the odds 35 to 41. Then do either 43 or 45. And again, they're using, this time they don't tell you the function, they graph the function for you, but you can still do the operations 43 and 45 using those 2 graphs. Then you're going to decompose some functions. Do any of the odds 47 to 53. And then a few application problems. Do any of the odds 55 to 61. Okay? Picture of a dog and cat there together too. All right, exploration. You could do some of those if you choose. I think you might find them sort of interesting. There's a conjecture there, 69. You don't have to do those, but if you just are hungry for a little more depth, go for it. Okay. Now, all right, we've got time, right? Yes, plenty of time. All right. Yeah, I know y'all are worried about that we might have to leave early or something, but don't worry. No, we wouldn't do that. Okay? I'm trying to find, I guess I do have to do this one here. Yes. And we're going to 1.9. And by the way, folks, this is the last section that we're going to do in this chapter. 1.10 is in this chapter, but that's on mathematical modeling and variation. I'm not saying it's not important. In fact, if it is important to your major, by all means read it. Go through that. I'll answer any questions you may have on it. But for our purposes, we're going to skip that section. So we're going to start from the current slide. Still doing functions in the graph. Now we're going to talk about inverse functions. Oh, is this something you've done before? Yes, of course you have. All of you believe that? What's the first, after you learned your counting, what was the first actual arithmetic operation you did way back in grammar school? Maybe even kindergarten, but probably grammar school. What's the first one you did? Adding, exactly. Boy, you worked on that too, I bet. You were memorizing all those additions and stuff, and you thought, finally got it knocked, and then what did they do? Turn around and undid it, didn't they? With subtraction. Subtraction undid addition. Guess what? You did an inverse function. Once you got subtraction down, you thought you may have it knocked. No. What did they have you do? Multiply. So then you have to start multiplying. And when you finally got all those multiplication tables down, what did they do to you? Dividing, which undid multiplication. So you did another inverse function. Now, much later sometime, I don't remember when this was, you started multiplying a number by itself, and we called that we just did it, squaring, okay? And then you could cube and fourth and fifth and power, so you did that. And then probably much later than that, you started undoing those things. How do you undo a square? Square root. You did an inverse function. So you've been doing inverse functions since grammar school. You just didn't call them that. Now we're going to call them that. Find the inverse functions informally. Now, frankly, to me, this is almost a waste of time, but supposedly from an education viewpoint, it's worthwhile, so we'll do it. And verify that two functions are inverse functions of each other. So we'll get a definition. Okay. All right. Then we'll use graphs of functions. This book loves graphing, don't they? To determine whether functions have inverse functions. Not a bad thing. And that graph is going to lead to a brand new test called the horizontal line test. We already had the vertical line test. What did that tell you? Whether it's a function or not, the horizontal line test is going to tell you whether it has an inverse function or not, whether the functions are one-to-one. And then we'll find the inverse functions algebraically. That's the way to go, not the guessing. But anyway, we'll do that. So what in the world is an inverse function? Let's start. Remember, there are many ways to express a function, right? One of those was sets of ordered pairs or tables, right? Remember that? So for instance, here's a function. Alpha of x is equal to x plus 4. Now let's say we have a very limited domain here. This one, 1, 2, 3, 4. Very limited. Nothing in between 1 and 2 or any of the others, just those 4 numbers. Now, what happens if you do alpha of 1? 5, alpha of 2, 6, x of 3, alpha of 4. Yeah, y'all got that done pretty good. Okay? That won't be on the test, by the way. Okay, never mind. All right. So what we could do is express this alpha of x. Here we did it as an equation. Here we saw it as its ordered pairs. Since these are the only input values, you could express this function as the set of ordered pairs 1, 5, 2, 6, 3, 7, and 4, 8. In this case, what we're going to do now is flip the order. That's what an inverse function is. It exchanges the x and the y, the input and the output, the independent and the dependent. Okay? And this gives you the inverse function. And how we express it is alpha to the minus 1. Now, earlier today, we did a variable with a minus power like that. What did that mean? No, that was 1 over that to the positive power. That's if it's a variable. or a number. If you see a function written there, that's not what that means. It means inverse function, which is not the same as 1 over. Definitely not the same. So your inverse function here, F inverse, would be the set of all numbers of ordered pairs. And what would they be? 5, 1, 6, 2, 7, 3, 8, 4. That is a set. Okay? Now what we don't have is a function to name it, a rule for it yet. But we know how to express it as ordered pairs. So it's a function from the set B to set A. What was your output becomes your input. What was your input becomes your output. Okay? It can be written as follows, and now they actually give it to us. The rule here then would be not x plus 4, but x minus 4. The inverse operation of the addition was your subtraction. So sure enough, when you put in a 5, you get a. And when you put in a 6, you get a. And when you put in a 7, you get a 3. And when you put in 8, you get a 4. So that's the inverse function. F inverse of x would then be x minus 4. Note that the domain of F, 1, 2, 3, 4, is now the range of F inverse. 1, 2, 3, 4. What was the range of F, 5, 6, 7, 8, is now the input or the domain of F inverse. You just switched the domain and range.
So
Okay?
what's the horizontal test for?
We'll get there in just a second. Yeah.
I'm trying to prove.
What's that?
What are we trying to prove that it's actually
Okay.
a function?
Okay. On a continuous function, okay, for you to be able to do an inverse, remember a function, what's true about a function? For every input, there's only one and only one output. Okay? For you to have an inverse function, then say if this was not the function we've been dealing with here, but you had a 1, 5, 2, 6, 3, 7, 1, 8. That would be a function with it, because 1 was a 5 here and an 8 there. So that meant for a continuous function, the function has to be, it cannot back up on itself. Because if it backed up on itself, then 2 outputs could be,
The same.
yeah, you got it. But you can't have that because then it would be an inverse function because it wouldn't. Yeah, you got it. That's it, exactly. Okay? But that's for continuous functions. These are discrete functions. Now this would be a continuous function if you put all the values in there. But how does that graph? The x plus 4 that we had, that's a line, slope 1, going through y-intercept of 4. This is slope 1 going through y-intercept of minus 4. Okay? I think it was anyway. Okay. So the function in its inverse is something sort of squirrely about that. Yeah, that's it. X. I'm having problems seeing the graph, but let's move on. No, let's do this. This is the, Note that the domain of F is equal to the range of F inverse and vice versa, as shown in this figure. And this is called the mapping diagram. Note also the functions F and inverse have the effect of undoing each other. Just like addition undoes subtraction, subtraction undoes addition, square roots undo square. Yeah, all that stuff, we've already been using that term. Now we're using inverse. That's what it means. So in the mapping, the domain of F, you F of X, then you operate on that with the X and add 4 to it, and that gives you F of X. When you're undoing that, you subtract 4 from whatever is in here and it gets you back to the same X you started with. Here's the problem with this that's driving me sort of nuts. They're calling the variable X in both cases. To me, this should be a Y, F of X equals Y. We all know that, right? So when you're going this way, that would be F inverse of y would be y minus 4. That makes more sense. But this book changes the variable back to x and does this way, which is okay, but it just makes it a little confusing. Okay? So, anyway. In other words, when you form the composition of F with F inverse, form the composition of F with F inverse, what F inverse did was take the y from F and move it back to x, and this is operating on that x, that takes it back to the same y again. So guess what? Well, they're exchanging the things here. You wind up with x. And when you take F inverse of F, well, let's do that. Let's actually do it. F of F inverse. Which is F inverse? X minus 4, remember? F operating on x minus 4. Remember what F was? Whatever's in here, add 4 to it. Right? So x minus 4 plus 4. Guess what? That's equal to x. Let's do the reverse of this. Let's do F inverse of F. F was x plus 4. F inverse subtracts 4 from it. X plus 4 minus 4. That's equal to x. Now, if you remember back when we did composition, we said something. Most of the time, F of G is not the same as G of F. Go back and look at last week's notes and stuff. You'll see that. It wasn't the case. But here we have a situation where you do get the same answer. And I said occasionally this will work, and when you do get the same answer, these are special functions. What are they? The inverse functions. When you get the identity function, when you do the composition of F with F inverse, or the composition of F inverse with F, you better get the identity function every time. That's what it means to be an identity function. Okay? So there's a test. If you're given two functions, say, are these inverses of each other? Just compose them with each other. Both ways. And if you get x both times, yep, those are inverses. So that's what we're going to do in example 1. Do we have time? 9:12. Oh, we have time. Y'all are fast, aren't you? Yes, I know you are. Okay. Find the inverse of f of x equal 4x. Can you give me a guess of what that might be? What is this function doing? F is multiplying your input by 4, so guess what the inverse might be doing? Yes, it's doing x divided by 4. Or you can say 1/4 of x, whichever. Okay, that's what we think the inverse is. Let's check it. Okay, let's do f of f inverse of x. Well, what do you plug in first? The innermost function, f inverse. F inverse was, that's f operated on x divided by 4. Well, what does the f function tell you to do? No. Multiply by 4. Whatever's inside, x, if I could write, x over 4, and multiply it by 4. Well, what happens then? You get x, the identity function. Let's do it the other way. F inverse of f of x. What do you plug in first? The innermost, so f inverse of, and f of x was 4x. And your f inverse function says take whatever's inside, 4x, and divide by 4. And guess what you get? X. Ding, 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 ding. You got it. It worked. Okay? Let me erase this quickly. We've got time, don't we? Oh, come on. Okay. Quickly here. The function f multiplies by 4. To undo that, we divide by 4. Okay? So the inverse function is x over 4. Okay? So f of f inverse is f of x over 4. That's 4 times x over 4. That's equal to x. And the other one, f inverse of f of x, is f inverse of 4x, which is 4x over 4, which of course is x again. And knocking my thing all over the place. No, I'm just kidding. Okay. Good deal. Thank you. Okay. I'll see you Thursday, briefly. we'll have the whole class, but I will be here and we'll wrap this up. And it looks like we may have the test either next Tuesday or Thursday. Oh, yes. All right. I knew that I would get cheers from that one. Okay. Good deal. Okay. All right. Let me end that screen.